Okay. Today we study section 4, Spline interpolation. The second topic, how to construct spline functions of degree-free cubic spline. Let me present some definitions. Mathematics definitions are the most important. Number one, a spline function is a piecewise polynomial function. Precisely, suppose we have n plus 1 points on the x-axis. Suppose T0, T1, Tn are given. These are the numbers. These points are on the x-axis. And suppose these points are in increasing order, satisfying increasing order. And also suppose these points lie in some open interval, say AB, less than B, and greater than A, And also suppose some integer, non-negative integer, some integer, K, non-negative, is given. Okay. According to the book, these points, we give them a name. Call these points nuts, not nodes, nuts. Then a spline function let me denote the spline function by S of degree K associated with the given nut, T0, T1, Tn is a function such that two conditions, A, S, this function defined on the interval AB, defined from A to B, and also has derivatives of order up to K minus 1. This condition says that the function S is smooth of order K minus 1. Condition B, on each of the following intervals, each of the intervals S is a polynomial of degree not greater than K. Okay. The intervals are from A to T1. Yeah. Let me draw a diagram. This is the x-axis. The interval A, B, say suppose A is here. B is here. B is here. The last T0 here. Then T1, T2, and so on. This point is a TK. This is a TK plus 1. This point is a Tn minus 1. Tn. The first interval is from A to T1. Over this interval, A to T1, the function S is a polynomial. Because A is open, so I put an open dot. T1 also open. Yeah, polynomial. Degree is less than K, or not greater than K. The second interval is from T1, now this time, including T1 to T2. T2, not including T2. From T1 to T2, a polynomial of degree not greater than K, because including T1. So, solid point. Then open here. Let me change this index Ti. Okay, this is I. Okay, not I, because I have used K here. K is the degree of polynomial. The third interval is T2, including T2, then to T3, open, and so on. The ith interval, Ti plus 1. Ti plus 1. Over this interval, polynomial S, this function is a polynomial. Yeah. Solid point. Then open. Then from Ti plus 1 to Ti plus 2, polynomial, and so on. Yeah, here. The second, from Tn minus 2, Tn minus 1, this interval, S is a polynomial. Now the last interval is, pay attention, is a Tn minus 1 to B, okay, including Tn, yeah. Over Tn minus 1 to B, polynomial. Okay. So pay attention. The first interval contains T0. The last interval contains Tn. Okay. Pay attention to this definition. Yeah. If a function satisfies these two conditions, then the function is a spline function. Spline function locally over an interval, it is a polynomial. Globally, from A to B, very smooth. The order is K minus 1. Okay, this is a spline function. Right. This is a definition number 1. Before I present definition number 2, let me show you 2 examples. Say, for example, a spline function. A spline function of degree 0. Degree 0, polynomial degree 0, it is a constant. So this is a spline function over each interval constant. So piecewise constant function. Yeah, the graph like this. This is the x-axis and y-axis. Y-axis is the function. Okay. A. Say A is here. A is here. B is here. Say the logs, how many? Let me give some concrete number. Okay. Say five logs. 5 logs. T0, 6 logs. T1, T2, T3, T4, T5, 6 logs. T5. Then spline function of degree 0, constant over each interval is constant. From A to T1, constant. So horizontal line. Yeah, here. The first interval from A to T1. This is open. Doesn't include the 2 endpoints. From T1 to T2, including T1, so solid point here. And then constant, open dot. T2 to T3, solid on T2, open at T3. From T3 to T4, solid at T3, then open at T4, and then solid. Let me see. The last interval is from Tn -1 to B, including Tn. So T4 to B, constant, open. Yeah. This is the typical. This is a graph of a typical spline function of degree 0. Now, how about degree 1? Yeah, let me draw. A spline function. A spline function of degree 1. Right. Again, I suppose there are 6 knots. This is a horizontal is x-axis, y-axis is function. Interval AB, T0 here, T1, T2, T3, T4, say T5. Over each interval, function S is a polynomial of degree 1. The graph is a line. So from A to T1, open. The graph is a line. Yeah. Degree 1. So S is in. Let me see. Go back to the definition. S is in this set. Now K is 1. So C0. That means that the function itself continuous over the interval AB. Yeah, C0 AB means function continuous. C1 from A to B, that means derivative continuous. Now 0, the function itself is continuous. From T1 to T2, a solid point at T1, then open at T2, a line, open at T2. From T2 to T3, solid point at T2, so solid, and then a line, open at T3. Similarly, from T3 to T4, solid, a line, open at T4. Then the last interval is a Tn -1 to B, including Tn. So the last interval should be T4 to B. So solid, and then a line, open. Yeah. this is the graph of a typical spline function of degree 1. Okay, it is a piecewise linear function. Okay, piecewise linear function. Okay, this is a definition 1. What is a spline function? What is a spline function? This is A. Now B. Use according to the book, we use this notation. Let's denote by this notation S spline n plus 1 is the number of the lots, and k over each interval. The spline function is a polynomial of degree log greater than k. Use this notation to denote the set of all spline functions of degree not greater than k associated with the given lots. Yeah. This set is a space satisfy the conditions required to be a space. It is a space. Okay, easy to prove it is a space. Definition number 3, C. Okay, now given a table of values of some function f. Given a table, yeah, x0, x1, x2, say x, because I have used m. Now, how about here? This time I use m. Function value x1, x2, and function value at xn. Now this time, these x values, they are distinct. The name for them is loops. Now this time, loops. Okay, loops. Not lots. Okay, lots means the t points. Loops, the x points. Given a table, and also the logs all are in the interval AB, all in the interval AB. Now the problem of finding a spline function from this set, finding a spline function from this set such that function value at x I is equal to function value of s at xi is equal to function value of f at xi. Of course, I is from 0, 1 to m. This problem is called a spline interpolation. Yeah. Let me make a remark. Now we have lots we have looked. These two sets may or may not be identical. Okay, let me put a remark. Looked, remark. Okay. The set T0, T1, Tn. This set is the set of lots, and the set of looks, the set of looks, x0, x1, xn. Yeah, this set is about looks. Okay. May or may not be identical. Usually different. Usually different. Okay, these are the definitions. These are the definitions. Two more examples. Yeah. Example number 3. Example number 3. The following functions. The functions. One polynomial. X polynomial degree 1. X2 polynomial degree 2, and xk polynomial of the degree k are all from this set. By definition, this set is the set of spline functions of degree k, right? Say for example, let me pick this one. I claim that this one is in this set. Okay, let me write this one in details. First, this guy is in, according to definition, it is a spline function. For a spline function, the spline function should satisfy these two conditions. First one, derivative has derivative of order up to k minus 1. Yeah, clearly this function is in k minus 1 over the interval AB, right? You can take derivative actually any times. So yeah, condition 1 clearly satisfied. Now, second condition, over each subinterval, is this a polynomial of degree not greater than k? Of course, right? This guy is equal to over the interval from A to not T0, but T1. Yeah. Over this interval, this function is this, a polynomial, right? If x is in this, right? Over this interval, it is a polynomial, right? Degree not greater than k. Yeah. How about the second interval? Second interval is T1 to T2. Yeah. Over this interval, this guy, of course, is a polynomial of degree not greater than k, and so on. Yeah, so on. Yeah. And the last interval is T n minus 1 to b, including Tn. Yeah, over this interval, of course, the function is sk. So over each interval, this function is a polynomial not greater than, with degree not greater than k. So therefore, by definition, this guy is a spline function of degree k associate with the lot T0, T1, Tn, right? Tn. So therefore, hence, right, this guy is in this set, the set of all spline functions. Yeah. This is example 3. Now, example 4. Example 4. Example 4. The following functions, they are named truncated power functions. Yeah, the power functions, the truncated, the following truncated power functions are x minus t1 power k truncated. So this is the normal power function truncated. Let me use this notation. Put a plus here. Yeah. X minus 2 t2 power, then truncated. I put a plus here, and so on. X minus tn minus 1, not tn, then power truncated. Okay. All these functions are from this set, the set of spline functions of degree k. Okay. What is the definition of a truncated power function? Here, the following is definition, where x minus ti, okay, general ti, I can be 1, can be 2, can be n minus 1. Definition is this, okay. If x independent variable greater than or equal to this not ti, then this function is the normal power. Yeah, x minus ti to k. Okay. If independent variable less than ti, then this function, the function value is 0. Yeah. The function so defined is truncated power function. Let me plot the graph of this function, truncated. X-axis, then y-axis is function, right? Y-axis. Suppose the lot ti is here, ti is here, ti is here. Okay. Now, x minus ti power, its graph is when x is ti, function value is 0. So through this part, the graph, and then let me arbitrarily draw a curve and suppose the curve to be the graph of this function. Yeah. Curve. Yeah. Curve. Yeah. All right. This is the graph of the normal power function, now truncated. When x greater than or equal to ti, on the right side of ti, truncated function is the normal power. So to the right of ti, the graph of this guy is this curve. Now, on the left side of ti, function value is 0. That means that replace this curve by x-axis. Okay. let me use a different color, say green. Yeah. Yeah. And then on the right side is the red curve. Yeah. This green curve is the graph of this. Okay. So replace the normal power with 0 when x is on the left side of Ti. Yeah, truncated. Okay, then truncated function, power function are from this set. That means that each truncated power function is a spline function of degree k. How to see this? How to see this? Okay, yeah, proof. Without loss of generality. Okay, only consider say x minus T1. K, power is k. Power is k. Then yeah, consider this special truncated power function. Yeah. Now I want to show that this guy is a spline function. Okay. First, let me prove first the truncated power function satisfy say condition B first. Over each interval, it is a polynomial with of degree log greater than k. Okay. Yeah. Condition B first. Condition B first. Condition B in the definition first. Okay. Now, x minus T1 k. Let me see. Over each interval, this guy should be a polynomial. Say the first interval from A to not to T0 to T1, A to T1. Yeah. Then by this definition, over this interval is on the left side of T1. So the function is 0. 0, of course, is a polynomial, right? 0. Okay. Now, then over the interval, including T1 to T2. Now this interval is on the right side of T1. On the right side, truncated function is normal power. So it is x minus T1 to k. So over this interval, truncated function is a polynomial of degree k. Now, the next interval from T2 to T3, but T2 to T3 is on the right side of T1, on the right side. So function is this, still this. It is a polynomial of degree k, and so on, right? Then the last interval is a Tn minus 1 to B, not to Tn, B. Then this interval is on the right side of T1, so truncated function is the normal power. Yeah. Therefore, condition B in definition of a spline function is satisfied. Now, let me prove condition A. What is condition A? Yeah. Condition A says that the truncated function should in this set. It means that truncated function should have derivative of order 0, order 1, order 2 until order k minus 1, and all derivatives continuous. Okay. Now, let me verify condition A in the definition of a spline function. That is, I want to show x minus t1. Yeah, this function is in k minus 1. K minus 1. By definition, x minus t1 to k plus is equal to over the interval a to t1. This function is 0 by definition. Then greater than t1, t1 to b. This guy is the normal power. So from the definition, x minus t truncated function clearly belongs to k minus 1 from a to t1. You agree? Because a zero has derivative of any order, and the derivative continuous. So this guy surely is in has smooth least of order up to k minus 1 clearly. Then over this open interval, x minus t1 k plus clearly is in this set t1 to b, right? From t1 to b over this open interval, this guy just a normal power clearly has derivative of any order and derivative continuous. So of course it's in this set. Now the question is, how about at t1 at this point? Okay. How about at this point? Okay. Let me denote this function by, say, by s. Okay. Denote this function by s. Now the question is, at t1, the function s has derivative up to order k minus 1. That means that derivative of order 0 at t1, derivative of order 1 at t1, derivative order 2 at t1, order k minus 1, k minus 1 at t1. XX, yeah, we need to answer this question, okay? Yeah. XX is not enough, and also we need continuous. Okay. As x as first derivative, as second derivative, and as k minus 1 derivative are continuous and t1. Okay, we need to answer these two questions, right? If I can prove these two, if these two questions, the answer to them are yes, then this function is in this set. Okay, now let me prove this. Let me prove derivative XX at t1 and also continuous at t1. Proof by induction. Okay, by induction. Okay, by induction to prove these two things. by induction. By induction. Okay. Okay. Now, let me denote the general. Yeah, the general derivative. Okay, by induction to prove S derivative order I at T1 x6 and derivative of order I, this function is continuous and at what at T1. Okay, by induction. Okay. Okay. Now, case 1. I is 0. Okay. Let me see. I is 0. That means that derivative of order 0 is equal to the function itself. Function itself, of course, a function at T1 is well defined. Function at T1, according to the definition here, function at T1, when x is equal to T1, the function is T1 minus T1, 0. So 0. Yeah. Yeah. This guy is 0. It's 0. Derivative of order 0 is continuous at T0. Derivative of order 0 is S. Of course, S is continuous at T1 from the graph of this function S. By S, I mean this. Okay, when you plot the graph of this guy, continuous at T1. Right. Now, case 1 is true. Now assume I minus 1, this case, the answer to these two questions are yes. Assume I minus 1, derivative I minus 1 times at T1 x6 and equal to 0, because here the derivative of order 0 is 0. So suppose derivative of order I minus 1 at T0 is 0, and also derivative I minus 1, this function is continuous. Continuous at T1, at T1. Now, I want to prove. Okay, we want to prove derivative of order I at T1 x6 and its value is 0, and derivative of order I is continuous at T1. Yeah, at T1. Okay. So I want to prove this. Okay, prove this. Okay, now let me first prove that derivative of order I at T1 is 0. By definition, derivative of order I at T1 actually is this limit. X approaches T1. I minus 1. Yeah, I minus 1. I minus 1 x. We have, by assumption, we know that this guy is 6 minus S I minus 1 at T1, then over x minus 1. Okay. By assumption, this guy is equal to 0. Equal to 0. Okay. Now I want to solve this limit x6, and the limit is 0. Because on the left side of T1, on the right side of T1, the definition of this guy different. So instead, to compute both side limit, I compute left-hand side limit, right-hand side limit. Okay, now let me compute left-hand side. X approaches T1 from the left, minus 0, then X minus T1. Okay. But on the left side, okay, when X less than T1, the function S, the truncated function is 0, right? By definition. So X less than T1, function is 0, derivative of order I minus 1 is 0. So this is X approaches T1, 0 minus 0, then over X. So limit is 0. Limit is 0. How about the right side limit? Right-hand side limit. X approaches T1 from the right side. S I minus 1, X minus 0. Okay. When X greater than T1, the truncated function is X minus T1, all okay. Now take derivative I minus 1 so many times. Then the result, take derivative I minus 1 times. The result is K minus 1. K minus I plus 2. Then X minus T1. The power is K minus I plus 1. So I plug in here. So this is a K limit. X approaches T1 from the right side. K minus 1. K minus I plus 2. X minus T1. K minus I plus 1. Then over X minus T1. Now cancel 1 X minus T1 from the bottom, from the top. I get this. Plus K 2 X T1. Cancel. So K minus I. We call that I less than or equal to K minus 1 because we want to solve. Yeah. So this guy has derivative up to order up to K minus 1. That means that I less than or equal to K minus 1. So K minus I greater than equal to 1. So when T approaches T1, this approaches 0. So therefore the limit is 0. So therefore derivative of order I at T1 is 6, and it is 0. It is 0. Okay, now continuous. Okay. Continuous. Okay. Take derivative I times whether or not is equal to derivative at T1. Okay. We just prove this guy is 0. Okay. Okay. Whether or not it is this. Again, left-hand side, right-hand side limit, because derivative, the expressions are different on the left side and on the right side. So therefore, left side. When X less than T1, the function S is 0, always 0. So this is a limit. 0. So 0. Yeah. How about the right side limit? Take derivative I times. Take derivative when X greater than T1, S is just the normal power. Then take derivative I times. It is K minus 1. K minus I plus 1. x k minus I. Okay. Remember I less than k, so this factor is at least x minus t. So when x approaches t1, so the limit is 0. So therefore, correct, this limit is 0. That means that as x is continuous at t1. So by induction, we have so that truncated function, yes, indeed, is in this set. Okay, this is condition A. Combined with condition B, therefore we see that this guy is a spline function of degree k. And similarly, to prove the other truncated power functions also in this set. Okay. Yeah, this is a fourth example about spline function. Okay. Yeah, let me stop here with example 4.